Hello, I'm Professor Steve Miller. Welcome back to Compressible Flow. Today we'll be continuing the subject of isentropic flows in this particular module. We'll introduce the idea of stagnation or total conditions for compressible isentropic flows. Total conditions and stagnation conditions, these words are used interchangeably and mean the same thing in the context of this course. We'll then apply this all-important concept to the idea of pitot tubes, which you've probably heard about previously in your previous aerodynamics or fluid dynamics classes. Then we'll look at a number of examples. Let's get started. I personally like to start with a fun quote. Here's one from Jonathan Strutt, the third Balin rally, which we previously discussed. He wrote, "Without encroaching upon grounds appertaining to the theologian and the philosopher, the domain of natural sciences is surely broad enough to satisfy the wildest imagination of its devotees. The work may be hard and the discipline severe, but the interest never fails, and great is the privilege of achievement." Let's now look at the idea of total or stagnation conditions. A total or stagnation condition is where we might, in our imagination or physically on a vehicle, bring the flow to rest, that is a zero velocity isentropically. For example, we'll try and bring the flow to rest at a stagnation point at the leading edge of a high-speed vehicle, or at some point in an isentropic flow, we might imagine we bring the flow to rest instantaneously without any losses. These are the so-called total or stagnation conditions for the variables that we look at, which are mostly thermodynamically related. So we'll try and develop these relations for the so-called stagnation or total conditions for the thermodynamic properties in particular, and a couple others which you'll find a little bit counterintuitive. This will yield one of the most useful tools and most used vocabulary within our field. In our previous classes, we developed this particular equation, which I've relabeled as 2O2 in this particular slide deck. So on the left, we have a specific enthalpy and a kinetic velocity. Remember, these must be constant in any particular isentropic flow because energy is conserved. Now, if we assume, which we haven't yet for this particular flow, that the flow is calorically perfect, then we can write H equals C sub Pt, where C sub P is the coefficient of specific heat at constant pressure, and T is the static temperature. And you'll see why soon. I keep calling T and H and variables like it static values, because they're not the total or stagnation values. Now, making the substitution in 202, we'll find C sub P T1 plus U1 squared over 2 is equal to C sub P T2 plus U sub 2 squared over 2. So I've just replaced the static enthalpies with the static temperature times C sub P, and I've made the assumption of calorically perfect gas. This is key, and remember this particular point. We can now use the ideal gas law, P equals rho RT, and that is substitute in the perfect gas law, the ideal gas law, into 203, and we'll come up with equation 204. Here we'll have, instead of C sub P, we'll have gamma R over gamma minus 1 times T1 plus U1 squared over 2 will be equal to gamma R T2 over gamma minus 1 plus U squared sub 2 over 2. You'll see why in a second I made this keen substitution. You'll recall the speed of sound relation, which we've had. C equals the square root of gamma RT, or square root of gamma P over rho. You'll see these types of variables, gamma over gamma minus 1 and R, in the previous equation. So using the speed of sound rule, I can write C1 squared over gamma minus 1 plus U1 squared over 2 is equal to C2 squared over gamma minus 1 plus U2 squared over 2. I can then write gamma over gamma minus 1 times P1 over rho 1 plus U1 squared over 2 equals gamma over gamma minus 1 times P2 over rho 2. Excuse me, this should be a row here in the notes where my cursor's moving, plus U squared sub 2 over 2. Now remember, because of our assumption that the flow is isentropic, that there's no heat transfer and no change in entropy. we should consider this fluid being brought to rest adiabatically to Mach 1 with the speed of sound, and we'll call that C sup star, or U2 equals C sup star. That we will substitute to the right-hand side, essentially, of 206. And so U2 will be C sup star, and we'll change, of course, leave the left-hand side the way it is. Here, C sup star is the so-called critical or reference condition, and it can be found in any given flow field given C and U. Now imagine we do the opposite situation, where the fluid is brought to rest isentropically instead of to, say, a reference speed of sound. We can then let T and U be the static values of temperature and velocity respectively. We can then find C sub Pt plus U squared over 2 equals C sub P T naught. This equation is derived from, say, 203, where we would have C sub P T1 plus U1 squared over 2 equals C sub P T2. On the right-hand side, we would eliminate U2 because it's 0 if we brought the fluid to rest isentropically, with no heat transfer, of course. And we would have C sub P T naught, and the left-hand side would be C sub P T1 plus U1 squared over 2. That's how we arrived essentially at equation 208. In the context of the notation in 208, you'll see that indeed we have C sub P T plus U squared over 2 equals C sub P T naught. Let's look at the notation carefully. C sub P, remember, is the coefficient of specific heat at constant pressure. T is the static temperature at some point in the flow. U is some velocity in the flow at the same location where T, temperature, is measured, squared divided by 2. On the right-hand side is the same coefficient C sub P, and T naught just simply represents the temperature if the flow is brought to rest to 0. This is a very powerful equation. You'll see through some examples of how it can be used. Remember, the stagnation or total conditions are those that correspond to conditions when the fluid is brought to rest isentropically. This last point is critical. Now let's try and use this particular equation and the previously developed relation from thermodynamics for calorie perfect gases that C sub P equals gamma R over gamma minus 1, where gamma is the ratio of specific heat, Cp over Cv, and R, of course, is the gas constant. Let's try and make this substitution for C sub P. And we'll make the substitution, and we find 209, first line of T naught over T. That's the stagnation temperature, or the total temperature divided by the static temperature, will be 1 plus U squared over 2 C sub Pt, which is 1 plus U squared over 2 gamma RT over gamma minus 1 through some simple substitution. Now the rest is algebraic simplification. And you'll see in here we've buried the speed of sound. So we'll have 1 plus U squared over 2C squared over gamma minus 1, because of course gamma RT is C squared from our previous derivation, which can simplify to 1 plus gamma minus 1 over 2 times U over C all squared. The wonderful thing now is you'll recognize U over C as the Mach number squared. We'll make that substitution and simplify it, and we find equation 210 in this slide deck, which you'll see is T naught over T equals 1 plus gamma minus 1 over 2 m squared. Let's remind ourselves of the notation. T naught is the temperature of the flow at a point of stagnation or imaginary stagnation. We call that the total or stagnation temperature. It's constant along these particular isentropic lines of flow, stream tubes. T is the particular static temperature for a given particular Mach number. 1, of course, is unity. Gamma is the ratio of specific heat, Cp over Cv, minus 1 over 2, times m squared. M is U over C, which correspond to the local velocity or the speed of sound, which corresponds to the local static temperature, T. This is an important equation, and we'll use it throughout the class. Now, we've previously shown isentropic relations from the previous class for particular conditions of T2 over T1, etc. Recall those particular isentropic processes, that the ratios of T naught, which is the stagnation temperature, divided by the static temperature, to the gamma over gamma minus 1, go as rho naught, the stagnation density over the static density, to the gamma power, is also equal to total pressure over P naught. Here, P naught is the pressure we would find if we bring the flow to rest isentropically. Rho naught is the density, total density or stagnation density, if we bring the flow to rest isentropically. Remember, T naught is the temperature which we find if we bring the flow to rest isentropically. They're related by these particular powers. So by using equation 210 and 211, we might be able to derive P naught and rho naught over rho and P, respectively. We can also do this more rigorously by using a very similar approach for, of course, the temperature relations of T naught over P naught, T naught over T. We can find the relations for P naught over P and rho naught over rho. I won't show these here because they follow almost exactly the same process. Or, if you wish, you can, of course, use gas laws to convert temperatures to pressures and densities, respectively. We can use the so-called isentropic relations to relate the ratios of T naught over T to other static variables. And here I've shown the reduction of these equations. And here I've shown the result of this analysis shown in bullet point 1, which is shown in all the major textbooks on compressible flow, which follow the same process of derivation as T naught over T, boxed as in this slide deck of equations 212 and 213. We find P naught over P goes as 1 plus gamma minus 1 over 2 m squared to the particular power of gamma over gamma minus 1, and rho naught over rho of 1 plus gamma minus 1 over 2 m squared to the 1 over gamma minus 1. You'll see they all have the same terms within the parentheses on the right-hand side. So if you're doing this on a calculator, you only need to know the Mach number of the flow and the particular value of gamma, Cp over Cv, and the rest is easy. You can only have to calculate the parenthesis and raise it to different powers on the right-hand side to find the particular ratios of the stagnation conditions over the static conditions. These relations are so important in our field that they've been tabulated in books published by, of course, the National Aeronautics and Space Administration. The first tables, which were widely used, came out of NASA Ames Research Center in, of course, California, which is a famous research center. We collectively call these today, informally, the Ames tables, because they're on desks of almost every aerodynamicist. They're also shown in my own form of these tables, which are given to you in the class handouts of this class, available on, of course, the class website or with your handouts. These are called the isentropic tables, and they're listed by Mach number in the left-hand column, and of course the ratios of P naught over P, T naught over T, and rho naught over rho in particular columns. In class, we'll go over these tables and explain them to you, and maybe later in some of these recorded videos. Let's now turn our attention to an application of this theory, which is on the purely isentropic flow through particular nozzles. And we'll focus on the nozzle problem throughout this course because it's wonderful to illustrate all these concepts. Remember, fluid dynamics is highly nonlinear, so you shouldn't remember too many rules of thumb because there's always an exception. We'll consider particular nozzles where the flow is completely isentropic throughout, meaning that there's no particular heat transfer and the change in entropy is zero. The primary purpose of any nozzle is to, of course, accelerate the flow. That is, it's taking some kind of energy and converting it into a kinetic energy which produces thrust. That is, it just accelerates the flow. Nozzles used in wind tunnels, propulsion systems, and many other types of applications. You'll probably be surprised in how many parts of your everyday life we use nozzles. Now, isentropic systems, remember, have a change of entropy of zero, and there's no losses in the flow, and there's no shock waves in the flow, which we'll consider in the nozzle problem and many other problems later in this course, where isentropic assumption breaks down. Now, many nozzles in practice have losses. And of course, the losses are due to the boundary layer turbulence, the shocks in the nozzles, and different kinds of flow phenomena. We will consider these losses and changes later in the course. Let's look at one particular example of isentropic flow calculation for stagnation or total conditions. Let's read the problem together to understand it. A perfect gas has gamma of 1.4. This means we have already made an assumption inherent in the problem, that the gases model is a perfect gas, and we can always close it with the ideal gas law of P equals rho RT. Gamma is 1.4. It might as well be air, where Cp over Cv is 1.4, the ratio of specific heats at constant pressure and constant volume. Now, at some point in the flow, it is moving at Mach number 3. Remember, that's U over C. The Mach number is 3, but from this information alone, we don't really know what the velocity is or speed of sound, so the problem's still rather undetermined. Now we know something about the static properties. The static properties of the flow at that particular Mach number are T equals 250 Kelvin. Notice I didn't say degrees Kelvin. The static pressure P is 101 kilopascals. And the density is 1.4077 kilograms per meter cubed. So we know the Mach number, we know it's a perfect gas, we know the ratio of specific heats, we know the static temperature, pressure, and density respectively. We are asked to find the stagnation or total conditions at T naught, P naught, and rho naught. Note that we denote the total or stagnation conditions of T naught, P naught, and rho naught by the naught values, that's subscript little o's. This is basically saying that if there was a Mach 3 flow in front of a flight vehicle and we brought it to rest isentropically and it stagnates on the vehicle, what would be the approximate temperatures, pressures, and densities if it was brought to rest isentropically, which of course never happens at Mach 3. But this is an exercise to think about this particular problem. Another way to view it would be to say we have a particular fluid element or volume, or parcel, if we use the correct historic terminology, a fluid parcel, and we brought it to rest isentropically, just in the air, what would its stagnation temperatures, pressures, and densities be? It's a simple calculation with, of course, the variables and equations we've defined. We've already found ratios of the total temperatures to static temperatures, the total pressures to static pressures, and the total densities to static densities, which we've shown on the previous pages. Let's look at the first form. We have 1 plus gamma minus 1 over 2 times m squared. We know m, which is 3. We know gamma, which is 1.4. We'll evaluate this term, and it turns out to be 1 over 0.3571. We do the same calculations for P naught over P and rho naught over rho. We'll find, respectively, for the pressure, stagnation pressure to static pressure, and stagnation density over static density ratios as 0.02722, and this is a typo, obviously. This should be a different ratio of 0.02722. So check my math here. For some reason, it was copied down by the student who typeset my notes. I apologize for that error. We'll find through the correct ratios, and here's the correct ratio. It should be, for density, 0.07623 for the right-hand side of 216. Nonetheless, we now have to put in from our problem definition T, P, and rho, which are the static values below the stagnation conditions on the denominator of the left-hand sides at 214 to 216 on this slide deck. Multiplying through, we'll have a stagnation temperature, 250 over 0.3571, of 700 Kelvin. We'll have a total pressure of 3710 kPa and a stagnation density of 18.5 kilograms per meter cubed. What does this mean? At standard conditions in Mach 3, the temperature goes up from 250 Kelvin to 700 Kelvin. That's a humongous increase in temperature just at Mach 3 in a supersonic flow. The pressure goes from a single atmosphere to about 37 atmospheres. Finally, the density goes from a small amount of 1.4 kilograms per meter cubed, which is a little bit higher than standard atmosphere, to about 18.5 kilograms per meter cubed, just by stagnating the flow isentropically. So you can see high temperatures and pressures can be achieved in our flows in Mach 3 in ideal ways. And this is true, of course, in realistic flows where there's shock waves in front of vehicles. Let's now turn our attention to another example of the so-called stagnation conditions by looking at a particular airfoil. Let's say here that air flows over an airfoil, which is pictured in figure 66, which states that, of course, the streamlines are going over an airfoil with moderate separation. So here's the airfoil in the middle of the figure. The streamlines are going from left to right, and we're in the fixed frame of the airfoil. Around the airfoil, in this colored pink region, is a turbulent wake and turbulent boundary layers. We won't consider the flow there because it's not isentropic, of course. We will consider, on a per stream tube basis, the inviscid type flow, meaning that the viscosity effects are negligible in the inviscid part of the flow field. So our equations should be holding generally anywhere on these particular streamlines. Now, the air moves over the airfoil as shown, as you've seen in previous experiments and visualizations. It says air, so it's reasonable temperatures and pressures probably, so we'll treat it as gamma 1.4 an ideal gas. The free stream air we see and measure perhaps that has a Mach number of 0.85, so this is a rather high speed subsonic flow. We'll write m infinity equals 0.85. We know that the static pressure in the atmosphere, P sub infinity, is 80 kPa. We'll find and estimate the largest pressure acting on the particular aerodynamic body. This m sub infinity and p sub infinity indicates the Mach number or pressures or temperatures or anything written with subscript infinity as the ambient values. So out here, way to the left where my cursor is, way to the left of the screen, on the left-hand side, is where we would measure Mach numbers 0.85 with a static pressure of 80 kPa. How do we solve this problem? Well, it's very likely that the highest pressure is acting at the stagnation point in the flow. So somewhere in here where my cursor is, the flow moves in from left to right and it stagnates on the leading edge of the airfoil. We'll estimate that as the highest pressure. This, of course, is the stagnation pressure in the flow. How do we do this? Well, we solve it with the simple stagnation pressure to static pressure Mach number equation for isentropic flow. In the upper picture of this page, I've drawn the leading edge of the particular airfoil shown on the previous slide, and the Mach number at 0.85 and 80 kPa, there should be an 80 there in my writing, excuse me, should come along and should stagnate at the leading edge of this airfoil, right here. We can use, of course, our equation for P naught over P equals 1 plus gamma minus 1 over 2 m squared to the gamma over gamma minus 1, which we just developed in this class. We know the Mach number and we know the static pressure. We simply put in these values and we find a static pressure ratio of P naught over P equals 1.604. We can then put in P, our static pressure, which is 80 kPa, and multiply by 1.604. That is, we multiply both sides at 2 and 8 by P, 80 kPa, and we'll get a total or stagnation pressure at the leading edge of the airfoil, which is right here in my cursor, and you'll find a value of 128.3 kilopascals. That's wonderful. So you see that the highest pressure we can estimate in this subsonic flow is about 128.3 kPa. Indeed, measurements confirm our predictions. Now, we can apply this particular concept to wind tunnel flows, not just an external aerodynamic problem, to make particular measurements in the form of compressibility. We've never made an incompressible assumption. It's very likely in your previous classes leading up to compressible flow that you derived a Pitot formula, a static or total type Pitot formula, which accounts for incompressibility, but it doesn't account for compressibility effects. The advantage of this approach is we don't have to worry about that. We can always use these same equations. Let's look at a particular device named, of course, after Pitot. This is the Pitot tube, and let's take the equation we've already developed and apply the Pitot tube formula and derive it for a particular device. So here in equation 219, I've repeated the equation we just used in the previous example. It's P naught, the stagnation pressure, or the static pressure, is equal to 1 plus gamma minus 1 over 2 times this Mach number squared to the power gamma over gamma minus 1, where gamma is, of course, the ratio of specific heats. Now let's take 219 and solve for Mach number. I've done the hard work for you, but you're welcome to try it. And you'll find m equals the quantity to the half power of 2 over gamma minus 1 times the quantity of P naught over P to the power gamma minus 1 over gamma minus 1 in quantity. That's what you have in equation 220. So if we know the static pressure in a flow, that could be the atmospheric pressure, an external problem, and we know the total pressure in the flow, we can directly calculate the Mach number of a flow. So here we have the Pitot formula. Now, we might write and interpret equation 220 in this particular device. This is what we call a Pitot tube. It consists of a hollow tube which is bent and it has a small opening towards the flow. The flow itself comes in from left to right along these streamlines. One streamline comes along and stagnates here at this position. The general velocity of the fluid in the probe is approximately 0. It comes down and goes to a manometer bank or perhaps some strain gauge or another type of device to measure the pressure inside the tube. So this particular tube is a Pitot probe because it does not contain static ports, which we'll talk about later. If this flow is subsonic, there's no shock wave in front of the tube and the flow stagnates without losses, and so we can use this isentropic relation which we already developed. There's also flow that goes around the tube and hopefully is rather undisturbed. So it's important to align these tubes in the flow, pointing in the direction of the flow, plus or minus a few degrees, of course. This flow has particular Mach number, pressure, temperature, and density, which are static or atmospheric values in front of the probe. We have to know that there's isentropic deacceleration coming up to the probe face. Otherwise, this probe won't be very useful, and we'll have to use other equations which we develop later. Let's look at some examples of these particular tubes. Here in figure 67 of this slide deck, I've written a pitot-static tube with a closed up or total and static pressure ports. So here's the tube itself, which I drew, and this part of the tube would be inserted into the wind tunnel, and flow would be coming from the lower left to the upper right. Here there's actually two ports, and so this is an annular tube and a center tube, which are of course hollowed out. This line here goes to the static pressure ports, which are on the outside of the tube, and this line here, which is just goes a manometer bank to measure the pressure, goes up through the center of the tube and measures the pressure, of course, at the leading tip of the pitot-static tube. This is called a pitot-static tube because it has 2 or 4 relative number of ports at this location on the side of the tube. The Pitot tube does not have, of course, these static ports. So at these locations, there might be particular static ports and make an annular tube down the middle of the regular Pitot tube. In this way, you can have multiple static pressure measurements on the side of the probe and a total pressure measurement at the leading edge. Here's the diagram of the so-called pitot-static tube, which you can see is a little bit different and is a visualization of figure 67. Here in figure 68, we see once again there's a streamline coming in and it stagnates at the center, and we get the stagnation pressure measured by the manometer bank by P0. At the sides of the tube, we would measure static pressures of the flow going over and below the tube. These you can see if you go through the lines like when you were a kid doing mazes perhaps, it measures static pressure. These are of course both closed, so we're measuring static pressure at the static pressure ports and a total pressure at the stagnation or total pressure port of the tube. You'll see that we always capitalize Pitot in the Pitot tube terminology because of course it's named after a person who originally measured the speeds of river flows with the Pitot tube concept, and we honor his invention today by calling all these devices after, of course, Pitot. A history on him will come later. Let's look at some examples of where Pitot probes are located on vehicles. This is a picture I took of a Boeing aircraft. And you'll see right here, we see 2 particular pitot-static tubes on the side of the vehicle. So these are, of course, calibrated into the flight computer, multiple of these pitot-static tubes to measure the velocity of the aircraft. So you see these are very practical inventions in aeronautics. Let's look at a few more curious examples. This particular pitot-static tube, which is mounted on the top of the X-15 vehicle, which is a X-plane from NASA to do hypersonics research. And you can see a list of interesting pilots here. And you might, if you're keen, see none other than Neil Armstrong, who is a particular test pilot of this vehicle, and is of course popular in movies. You can also see a number of other famous test pilot names, and some of these also became astronauts in the United States. You can see on this particular Pitot tube mounted in front of the cockpit here, windows, that it has indeed a very large stagnation port and very small static ports. You might wonder why they made it so large. We'll discuss that later in the class. Here's a very peculiar and interesting version of the Pitot static tubes. This is in the United States Air Force Museum in Dayton, Ohio, and I've taken these particular pictures of the F-117 stealth bomber. Up in front of the aircraft, you'll see these particular points coming out, and there's multiple of them. And these are actually Pitot static tubes, which are designed for stealth. They have a particular shape around them to try and reflect and absorb electromagnetic waves efficiently so it's not returned to the radar. Let's look at a close-up of these. Here's one particular tube, here's another one, and here's another one. You can see at each one of these there's a tiny little hole, and it's shaped with a rather straight pattern, and these are, of course, are measured and put there to obtain correct air velocities. You can see an A-10 in the background, rather fun. If you're ever in Dayton, Ohio, I recommend going to this museum and taking a whole day to walk through it. Many people take 2 to 3 days to see every exhibit. Here's another famous aircraft, which is the predecessor to the SR-71, and I also took this photo in the same museum. And you see it has a long tube off the leading edge of the, of course, like cone-like fuselage in the front. And indeed, out here, it has an arrangement of probes, which is just off the figure itself, of pitot-static probes. This was the YF-12 interceptor, and indeed the SR-71 program had a component of YF-12, which was a supersonic interceptor. In fact, this aircraft you see here was able to deliver a missile supersonically in supersonic flight, looking down at a forest at a supersonic moving target. This was incredible at the time, and it was really pushed to intercept, of course, Soviet supersonic aircraft coming to deliver nuclear weapons to the United States. Here's a picture of the tube. I stood right by the front of the aircraft, so if we zoom into this part right here, you'll see that once again we have the long tube. There's a stagnation port here and here, and if you look very closely, there's tiny little holes in the tube that are the static pressure ports. And so this was key for these types of vehicles, so they could, of course, get their airspeed correct. Let's look at some examples of the famous Pitot static tube problem. And I've made a typo here. I should have capitalized Pitot. That was rather rude in his memory. Please don't make the same mistake. The static pressure and temperature in the flow are measured as 80 kPa at 12 degrees Celsius, respectively. So I've given you P and T of 80 kPa and 12 degrees Celsius. We now measure the difference between the total and static pressure as 200 milligrams of mercury. And we're asked to find U infinity, that is the ambient velocity and Mach number from the measurements of the Pitot static tube. Now remember from your fluid statics lectures in your previous classes that you'll find for a manometer bank, the pressure, the total pressure, P naught, minus the static pressure, that is the differences in the heights of the mercury, goes as the density of the mercury times the gravitational constant of the particular body we're measuring on, times the height change. So here I've given you the density of mercury, which is 13,580 kilograms per meter cubed. The gravitational constant is in meters per second, which is 9.81. And of course, the height of mercury, delta H, we measure will be 0.2. We find a delta P total, difference between the total pressure port and the static pressure port, as the density of mercury, 13,580 times 9.81 meter per second squared, times the height, which is 20 centimeters. And we'll find a value of 26.64 kilopascals. That's rather fun. So now we know the differences, and we know one of the static values. So we can, of course, find the stagnation value. What's next? Well, we need to find the appropriate ratio of stagnation to static pressure so we can derive the Mach number from our Mach number stagnation pressure to static pressure relation. I'll write it out like this. If I write P naught over P minus 1, I can then rewrite that as P naught minus P over P, which will be equal to 26.64 over 80 kPa, and I can find P naught over P as a value of 1.3331. I now know P naught over P, and I can use my equation of m equals the square root of 2 over gamma minus 1 times P naught over P to the gamma minus 1 over gamma minus 1. And I'll put in my values for P naught over P, stagnation pressure over pressure, measured by the pitot probe. I'll put that in here and I'll evaluate, and I'll find an ambient Mach number of 0.654. So from the total pressure to static pressure measured by a pitot tube, I'm getting a Mach number of 0.654. That's the general Mach number of the aircraft if it's flying, of course, subsonically. We can now find the actual velocity of the aircraft in meters per second through the Mach number relation. Remember, m equals u over c. Solving for u, I can write u infinity equals m infinity divided by c infinity. This is the ambient global Mach number of the aircraft. I would have to know something about the ambient temperature around the aircraft. Perhaps I know the static temperature at the altitude which the aircraft is flying. I can substitute in square root of gamma r T infinity for C infinity, and now I know Mach number, I know gamma, I know R, but unfortunately I do not know the static temperature. That I'll have to find in another way that is beyond, of course, the pitot probe. I'll give you the value, of course. It's 285 Kelvin at the particular altitude. So this is something that you can't derive from these particular formulas. You have to have some other kind of sensors to find it. So let's fill in the data. Mach number 0.654, gamma 1.4, gas constant 287, static temperature at altitude 285 Kelvin. We will find the velocity of the particular flight vehicle measured by this pitot probe as 221.3 meters per second. So you see, to find Mach number, we had to use P naught over P from the probe, which is something we typically measure to find, of course, Mach number of an aircraft. The same things can be used to find Mach number and velocity in a wind tunnel. It's exactly the same concept. And of course, it's very much like how Pitot himself found velocities of river flows with, of course, a pitot type probe. You'll note also to find the ambient velocity, I required a static temperature at the probe location. Let's now turn our attention to examine errors in the so-called incompressible and compressible forms of the Bernoulli equation. Let's look and return to Daniel Bernoulli, who the equation is named after. It's not named after his father or his brother, who were also active mathematicians and worked in fluid mechanics. In fact, there was some jealousy between Daniel Bernoulli and his father and his brother because he had, of course, the most success. Here he is pictured in an etching on the right, and he was born in 1700 and passed away in 782. Like Leonhard Euler, he was, of course, Swiss. He was a mathematician and physicist and one of the most and many prominent mathematicians in the so-called Bernoulli brothers. He applied math, mechanics, especially the fluid mechanics, and he's known, of course, for his probability work and statistics. In the Bernoulli principle, which is a particular example of conservation of energy, we applied to this particular class. He was indeed, during his life, a great friend of Leonhard Euler, which we already talked about. And he wrote the beautiful book, Hydrodynamica, which you can find free copies online as scanned PDFs, if you can read them. And this was actually the original basis for the theory of the kinetic theory of gases. And with Euler, he developed the so-called Euler-Bernoulli beam equation, which you might have heard about in your structural classes. Let's now look at the particular error in the incompressible theory relative to compressible theory with Mach number. This is our goal, and we'll try and plot that error with increasing Mach number. Now, the classical Bernoulli result from your previous classes was that the velocity of the fluid, if measured by a pitot probe, was the square root of 2 of the quantity of the measured stagnation pressure minus the static pressure divided by the density. Here, density, rho infinity, is the same everywhere in the fluid. This is, of course, wrong in incompressible flow problems. Excuse me. Now we need to find the corresponding equation that includes compressibility effects, which we've already built the framework for. You'll see in this particular equation, P naught minus P, we'll try and replace that particular form with our own. We'll find P naught minus P will go as, if I write it, as P over P naught over P minus 1, which I can rewrite as 1/2 rho u squared times 2p over rho u squared times the quantity of 1 plus gamma over minus 1 over 2 m squared to the gamma minus over gamma minus 1 minus 1. In 227, you'll see the P naught over P quantity is replaced by, of course, our compressible flow relation for stagnation pressure over static pressure. And we'll have 1 plus gamma minus 1 over 2 m squared to the gamma over gamma minus 1 minus 1. The minus 1 is carried over. So we're left with wondering, how did we change P into this particular form? Well, you can see we wrote 1/2 with 2, that crosses out. We have rho u squared over rho u squared in P. You'll see why I've written it this way momentarily. If we now replace P, rho, and u in the second term of 227, we will find this particular equation. Once we replace P, rho, and u in the second particular term with, of course, our Mach number relations, we'll find P naught minus P goes as 1/2 u squared, which is that first term, times 2 over gamma m squared with the third term in 227. Now, if we search for and solve for u and replace it as u infinity, we'll find equation 229. This is actually a lot of work, and from the previous example, we should, and much easier, found Mach number and then solve for Mach number for the particular temperature relation. But here the advantage, of course, is that we've eliminated temperature by using density and pressure in our formula. So essentially, the ideal gas law could be used to recover this equation 229. We'll then find u infinity equals the square root of 2 P naught minus P over rho times the quantity shown here from the previous equation. So we solve for u infinity now. Now that we have u infinity, we have u infinity estimated from compressible flow theory in 229, and the result you previously derived in your classes in fluid mechanics and aerodynamics, which is u infinity of 2 P naught minus P over rho. You'll see, look carefully between 229 and 230, the compressible form and the incompressible form. You'll see they're exactly the same equation, except for, of course, the second term in the squiggly brackets. This indeed accounts for some kind of error between the incompressible and compressible forms, which is a function of Mach number. That's beautiful. So we can now define an error. Let's call our error epsilon, and epsilon will go as the magnitude of the compressible velocity minus the incompressible velocity divided by the compressible velocity, which of course is the correct answer. And that'll go through simplification as the magnitude of 1 minus u incompressible, which is 230, divided by u compressible, which is 229. Let's substitute in these relations, and I simplified it for you, and you'll find that the error goes as the magnitude of course, 1 minus 2 over gamma m squared times this quantity of 1 plus gamma minus 1 over 2 m squared to the gamma over gamma minus 1 in squiggly bracket half power. So you'll see the error entirely depends only on the Mach number and gamma, which makes sense because in 229, the term which accounts for the error between the incompressible and compressible results only involves m and gamma. So that's a good check to make sure our calculation is correct. You'll also note that the error is, in fact, non-dimensional, which makes sense because we defined our error as a non-dimensional parameter, a velocity divided by a velocity. Let's now plot equation 232 in the slide deck. Here's figure 75, error with Mach number of measured compressibility effect. The x-axis is Mach number from 0 to 0.6, and the y-axis is the error which we just derived in the previous equation. We'll set gamma 1.4 for error, and we'll vary Mach number. If we plot the equation, of course, it rises. So at Mach 0, of course, the arrow is 0 because there's no difference in the velocity 0. And you can see that in these equations if we set m equal to 0. And there's also no difference in the pressure, so that would be 0. Density is a positive constant in the incompressible case and varies in the compressible case. You'll see now that the error increases all the way to about 1%. near Mach 3. So this is why we say that the onset of compressibility in general flows, that is just general rule of thumb, is about 1% at Mach 3. So if you care about an error of 1% or more, you should use compressible formulations for these types of flows. If you care about absolutely no error, having zero error in the calculation, you can just use the compressible formulations throughout the entire Mach number range. It is highly efficient to use incompressible formulations, especially in computational fluid dynamics. So it would be very advantageous to make the incompressible assumption for low Mach number, where your errors are going to be, of course, on the order of 0.1%. You can see this rises greatly, and if we plot it all the way out to, say, Mach 1, the error increases dramatically. Nonetheless, this error formulation becomes flawed because of the onset of shock waves at higher Mach numbers, especially at transonic and supersonic speeds. So this error formulation is only valid for, of course, these low to mid-speed subsonic flows. Here I show another example for the class, and I'll let you follow this example on your own. In this class, we derived and explained and defined the so-called stagnation or total conditions, which we remember are used interchangeably. They are the conditions where we, in our imagination or physically, in some flow situations, bring the flow to rest. They are a property which is constant along the streamlines or stream tubes in fluid parcels as long if the flow is isentropic. We then applied these equations to the famous Pitot static tubes and Pitot tubes in two particular problems and showed examples for, of course, calculating Mach numbers and flight velocities of aircraft, and of course doing measurements in wind tunnels. Then we showed a few particular examples. Thank you very much for your time today. I'm Professor Steve Miller.